Welcome back. In this video, you will learn about polar coordinates. Let's get to it. Alright, so up until this point in calculus, and probably all of your other math classes, you have only been graphing in the rectangular coordinate system, where you have points that have an x-coordinate and a y-coordinate. And we've been graphing those points using equations in either rectangular form, or more recently here in Calc 2, in parametric form. But now what we're going to do is look at an entirely new coordinate system, or at least for most students at this point, it's entirely new. Sometimes you're introduced to this in pre-calculus, but for most people, it's brand new here in Calculus 2. And this brand new coordinate system is the polar coordinate system. And unlike the rectangular coordinate system, the polar coordinate system is going to rely a lot on angles. And so as you can imagine, since we're going to be working with angles, there is going to be some trigonometry involved as we look further into using polar coordinates and graphing polar functions. And so that might not sound too exciting, but what you're going to find with the polar coordinate system is that it's going to make graphing certain types of graphs a lot easier. In particular, it's going to be great for curves that are circular. And so here's how the polar coordinate system works. We start with what we call the polar axis. And you can think of the polar axis as being the replacement for the x-axis from the rectangular coordinate system. All right, so the x-axis was a horizontal axis, and the polar axis is also a horizontal axis. Now the polar axis extends in both directions from a point that we call the origin, or sometimes you'll hear it called the pole. And I'll label that point with O, just so you know that that point right there is the origin or that pole. Now I know I said that the polar axis extends in both directions from the origin, but to keep things simple for this diagram here, I only have it extending in one direction, but just know that it does extend in both directions from that origin or from that pole. All right, and then what we do in the polar coordinate system to plot points is we first measure an angle from the polar axis. Now that could be above the axis or below the axis, it depends on the angle. But let's say that we have this angle right here. The angle from the polar axis to this line, we would label with theta. That is going to be our angle. And then this other line that the angle measures to is not going to extend forever. It's going to stop at a particular point, which is going to be the location of a polar coordinate, or a point in the polar coordinate system. So I'll draw that point right here. We're going to label that with P. That is going to represent a point in the polar coordinate system. And notice that this point is a particular distance from the origin, right? That point O. This distance between these 2 points is what we call the radius, or the measurement R, for a polar coordinate. And it's this measurement R, the radius, and this measurement of the angle, theta, that make up the components of a polar coordinate. Right, just like in the rectangular coordinate system, our coordinate points had an x-coordinate and a y-coordinate. Well, for the polar coordinate system, we have a coordinate for r, the radius, and a coordinate for theta, the angle. And so we would say at this point P is equal to a coordinate point of r, comma, theta. That is the form of a polar coordinate that we would graph in the polar coordinate system. Instead of having an x-coordinate and a y-coordinate, we have a radius and an angle. All right, and so that's the very basics of how the polar coordinate system is going to work. But when we actually go to plot polar coordinates, we are going to use a grid system, just like we use when we graph rectangular coordinates. However, instead of using a coordinate system made up of squares, when we graph in the polar coordinate system, we're going to use a grid of circles, which is going to take advantage of the fact that polar coordinates are made up of a radius and an angle. And so here's what that grid will typically look like. This is the grid system that you will typically see when you want to graph polar coordinates. You can see that just like with the rectangular coordinate system, we have 2 axes, a horizontal axis and a vertical axis. This horizontal axis is our polar axis. Right now you can see that it extends in both directions from the origin. This point in the middle is that point O that we call the origin or the pole. And you'll notice that origin is the center of these concentric circles that make up this grid, right? Each of these circles that you see are all centered around that origin. So what that tells us is that the distance from the origin to any point along each of those circles is going to be the radius of those circles. So what we do is say that this first circle that we see represents a radius of 1. This second circle that we see would represent a radius of 2, and this third circle would represent a radius of 3, and so on. We could extend this graph to be bigger and bigger to include more circles. All right, and then you'll also notice that we have these lines that are crossing through the origin. Each of these lines represents an angle of theta that we might have for a polar coordinate, which will help us graph our points more quickly. And you'll notice that this vertical line right here that crosses through the origin, this would be the replacement of the y-axis from the rectangular coordinate system. This doesn't really have a fancy name like the horizontal axis does, which is our polar axis. We just call this axis theta equals pi divided by 2, because this line is where the angle for theta would be pi divided by 2. Okay? Now, typically when you're graphing in your own work and you don't have this system to work with, you will have to draw these circles and draw those lines yourself, depending on what values of the radius or the angle that you have for your points. But this is the general look of the polar coordinate system that you will use to plot polar coordinates. All right, but there are a couple rules that you need to be aware of with regards to graphing polar coordinates in this system. And to demonstrate those rules, we're going to look at this point. I'm going to say p is equal to 2 comma pi divided by 3. This is a polar coordinate that we can plot in this system. The radius r is 2, and the angle theta is pi divided by 3, right? A polar coordinate has the radius first and then the angle. All right, and so when you plot a point like this in the polar coordinate system, I recommend that you start with the angle. And so let's take a look at the rules for measuring the angle of our point theta. When theta is greater than 0, or when theta is positive, you're going to measure that angle counterclockwise from the polar axis. So you're going to start right here on the right side of theta equals pi divided by 2. You start at this polar axis, and you will measure your angle counterclockwise from that polar axis. That's when theta is greater than 0, or when theta is positive. But if theta is less than 0, or when theta is negative, you're going to measure your angle clockwise. So you would start at your polar axis here and measure this way, the same direction that the hands of a clock would move. All right, so in this case for our point, our angle is positive pi divided by 3. That means we're going to start at our polar axis and measure pi divided by 3 counterclockwise from that axis. And so that would be at this line right here. This line represents the angle pi divided by 3. So we know our point is going to be somewhere along this line, but then exactly where it's going to be in relation to that origin is going to depend on the radius. In this case, our radius is 2. And so now let's look at the rules regarding the radius when we plot these points. When the radius is greater than 0, meaning that it's positive, you're just going to plot your point right along the circle that has the corresponding radius. All right, so for example, this point 2 comma pi divided by 3, we know that our angle takes us to this line right here, and then the value of our radius is 2, so our point is going to be on the second circle. This circle represents a radius of 1, so right here would be 1 comma pi divided by 3, but then this point right here on the second circle is our point 2 pi divided by 3. So we can actually plot our point now. This right here is our point P. Our radius is 2, and our angle is pi divided by 3. And so that was pretty simple because our radius was positive. But if your radius is not positive but negative, if r is less than 0, then what you have to do is reflect that point from where it would have been if the radius was positive. All right, so it doesn't affect the angle. Notice that we still measure the angle first. We measure the angle from the polar axis. We measure the radius, but since it's negative, we then reflect it to the other side of the circle. So for example, if this point wasn't positive 2 pi divided by 3, but negative 2 pi divided by 3, we would measure to this point first. We would measure our angle. That's not going to change. But then instead of being at this point along this circle where the radius is 2, we're going to reflect it to the other side, which would be right here. And so this point right here, which is 1, 2 away from the origin, would be the point negative 2 pi divided by 3. All right, so if your radius is negative, you just have to reflect what your point would have been if the radius was positive to the other side of the circle. All right, so those are the basic rules for plotting polar coordinates in the polar coordinate system. Now let's take a look at actually plotting some other points using these rules. All right, so here's our example. We're going to be plotting all 6 of these points here, points A, B, C, D, E, and F. We're going to plot them in this polar coordinate system by measuring each angle and each radius. And so let's start with point A. Let's plot this point in our coordinate system. A is equal to 1 comma pi divided by 4. So our radius is 1 and our angle is pi divided by 4. So what we want to do is start at our polar axis on the right side, and we're going to measure our angle first. So our angle is pi divided by 4. So if we start here, that's going to take us to this line right here, halfway in between 0 and pi divided by 2. All right, so we know that we're going to be along this line where the angle is pi divided by 4. But then our radius is 1, which means our point will be along that first circle. This first circle is where the radius is 1, this second circle is where the radius is 2, and this third circle is where the radius would be 3. So our point of 1 comma pi divided by 4 will be right here on our graph. That is going to be point A. All right, we have that angle of pi divided by 4, and we are on our circle where the radius is 1. All right, so that's point A. Now let's move on to point B. Point B is at 2 comma 2 pi divided by 3. Once again, we want to start with the angle. So if we start at the polar axis, we're going to measure our angle in the counterclockwise direction until we get to 2 pi divided by 3. That is this line right here. But then our radius is 2, so our point is going to be along the second circle. So the point B will be right here. That is our point B. All right, our angle is 2 pi divided by 3, and our radius is 2. We are along that second circle, which means that this point is a distance of 2 away from the origin. All right, so that's point B. Now let's look at point C. Point C is 3 comma negative pi divided by 2. All right, so in this case, our angle is negative. So we're not going to measure our angle from the polar axis in the counterclockwise direction. We're going to measure it in the clockwise direction. All right, so negative pi divided by 2 means that we are going to move pi divided by 2 in the clockwise direction. That's going to take us to this line right here at 3 pi divided by 2, right? Pi divided by 2 makes up 1/4 of a circle. So that means if we're starting at the polar axis and moving in the clockwise direction, that we will end up along this line, 1/4 of a circle. All right, so we know that we're along this line, but then our radius is 3, so that means that we are going to be 3 units away from the origin. And so if we count our circles, we have 1, 2, 3, so our point C will be right here. That is the point 3 comma negative pi divided by 2. So now we've plotted C. Now let's work on plotting D. D is equal to negative 2 comma pi divided by 3. So we'll start with the angle. Our angle is positive, so we are going to measure in the counterclockwise direction. So we start at our polar axis, measure up to pi divided by 3. That's this line right here. But then our radius is negative 2. All right, so since the radius is negative, our point is not going to be right here, right? This is 2 away from the origin, and we are along that angle of pi divided by 3, but since that radius is negative, we need to reflect this point to the other side of the circle. All right, so instead of being at this point right here, we are going to be down here. This is going to be our point D, which is negative 2 pi divided by 3. All right, so that's point D. Now let's look at point E. Point E is at negative 1 comma negative pi divided by 4. So in this case, both the radius and the angle are negative. So that might seem a little bit tricky, but all you have to do is just start with the angle and then worry about the radius. In this case, we have negative pi divided by 4. So since the angle is negative, we're going to start at the polar axis and measure in the clockwise direction. We are going to go below the polar axis instead of above it. And negative pi divided by 4 will take us to this line right here, where we have 7 pi divided by 4. Right, in the positive direction, pi divided by 4 is halfway between pi divided by 2 and 0. So negative pi divided by 4 will be halfway between 0 and 3 pi divided by 2. So we know we're going to be along this line right here, where we have 7 pi divided by 4. But now let's take our radius into account. We have negative 1. So if that was positive, we would be at this point right here, where the radius is 1. This would be 1 and then negative pi divided by 4. But since that radius is negative, we need to reflect that point to the other side of the circle. So instead of being at this point right here, we are going to be at this point right here. This is going to be our point E, which is -1, -pi divided by 4. Okay, so that was E. Now finally, let's look at F. That's going to be the last point that we want to plot. F is equal to 1, -3 pi. All right, and so let's start with our angle. The first thing to notice here is that this angle is bigger than 2 pi, which seems to not be included in this system, right? We have one full circle, which makes up 2 pi, or 360 degrees. I don't have 2 pi written here, but this angle right here, where theta is equal to 0, would also be where theta equals 2 pi, because if you start at the polar axis and come all the way back to it, you've made a full circle, which is 2 pi. And so if our angle is -3 pi, we know we're going to at least make one full circle, and then we're going to have another measurement of pi. All right, but it is negative, so we're going to start at the polar axis and move clockwise. So we'll start here, we'll make one full circle, that's -2 pi, and then we still have another -pi to account for. And pi is a semicircle, or 180 degrees, so -pi will take us from the polar axis right here. We're going to be along this line where the angle is pi. All right, so that's where -3 pi will be. And then our radius is 1, so we know that our point will be at this point right here along this first circle. So our point F will be right here. That is the point 1, -3 pi. Okay, so now we have plotted all of our points. Hopefully these 6 points served as a good demonstration on how you plot coordinate points in the polar coordinate system. I always recommend that you start with the angle and then take care of your radius. Now you might have noticed, as we were plotting these points, that it's going to be possible for us to represent the same point multiple ways with polar coordinates, right? For example, point E right here, this was -1, -pi divided by 4, but we could also find E by just measuring this angle right here, which is 3 pi divided by 4, and then using that radius of 1, right? We could represent that point E with a completely different coordinate point, where we have a positive radius of 1 and a positive angle of 3 pi divided by 4. That's going to take us to that same point. And that would be true for all of these other points as well. We could find other sets of coordinates that will give us the same point in this system. And so unlike rectangular coordinates, where each set of an x-coordinate and a y-coordinate gives us a unique point, that's not going to be the case for polar coordinates. There's going to be multiple different ways to represent the same point in this system. Okay, and there are some rules that you can use to find equivalent points for points in a polar coordinate system, but before I show you what those rules are, I want to take a look at a couple more examples of some equivalent points so that you can start to see the pattern in the polar coordinates that makes them represent the same point. Alright, so here I have a few sets of some polar coordinates that are actually going to represent the same point in the polar coordinate system. And so let's start by taking a look at our first set of polar coordinates. We have 2, pi divided by 4 and 2, 9 pi divided by 4. And so if we plot our first pair of polar coordinates here, our radius is 2 and our angle is pi divided by 4. The angle of pi divided by 4, if we start at our polar axis, will take us to this angle right here at pi divided by 4. And since our radius is 2, that will take us to this second circle. So those polar coordinates take us to this point right here in our polar coordinate system. So I'll plot that point. And now let's take a look at this second pair of polar coordinates. In this case, we have the same radius. Our radius is still 2, but then our angle is 9 pi divided by 4. Now what's important to realize about that angle is that 9 pi divided by 4 is bigger than 2 pi, right? 2 pi is an angle that makes up a full circle. If we start at the angle of 0 and make a full circle, that would be an angle of 2 pi. And we know that 9 pi divided by 4 is bigger than 2 pi because 8 pi divided by 4 would be 2 pi, right? 8 divided by 4 is 2, so this would be 2 pi. And so 9 pi divided by 4 is bigger than 8 pi divided by 4. In fact, if you were to add pi divided by 4 to 8 pi divided by 4, that would get you your angle of 9 pi divided by 4. So really, this angle right here is just 2 pi plus an additional pi divided by 4. So if we were to measure that angle on our polar coordinate system, starting at our polar axis, we would make one full circle of 2 pi, and then we would go an additional pi divided by 4. that will take us to this angle right here. And then we have the same radius, so our point is going to be right here, the exact same point in the polar coordinate system. And so what we learned from these 2 points is that if we have a polar coordinate, we keep the radius the same, but then add 2 pi to the angle, the resulting pair of polar coordinates will represent the same point in the polar coordinate system. As long as your radius is the same and you're just adding 2 pi or even subtracting 2 pi would work as well, to that angle, you're going to have equivalent polar coordinates. All right, so that was our first set of polar coordinates that represent the same point. Now let's look at our second set. We have -2 comma pi divided by 4 and +2 comma 5 pi divided by 4. So now let's start with this first one here. This is very similar to the last point that we plotted, except our radius is negative. So let's plot this. That angle of pi divided by 4 will take us to this angle right here, and our radius is -2. So we're going to be along this second circle, just like we were before, but since it's negative, we're going to reflect that to the other side of the polar coordinate system. All right, so we're going to be at this point right here instead of this point. So this right here is our point -2 pi divided by 4. All right, but now if we look at our other pair of polar coordinates, we have 2 comma 5 pi divided by 4. If we were to plot this point in this system, let's first measure the angle of 5 pi divided by 4. I'll start at the polar axis here, and we'll make our way around until we get to 5 pi divided by 4, this angle right here. And if you weren't sure where that was, if you don't have a labeled system like this, just know that 4 pi divided by 4 is pi. So we know that this is at least going to take us to pi, and then we have to move an additional pi divided by 4 to get us to 5 pi divided by 4. All right, and you'll notice that that angle is exactly where our other point is, right? And we're going to be along that same circle because the radius is 2. So we measure our angle, that's this line right here, 5 pi divided by 4, and the radius is 2, so we move to the second circle. This pair of polar coordinates represents the exact same point as this pair of polar coordinates. And so what we learned from this pair of polar coordinates is that if you negate your radius, in this case we went from -2 to +2, and add pi to your angle, in this case pi divided by 4 plus pi gives us 5 pi divided by 4, then that resulting pair of polar coordinates will represent the same point. All right, so you negate the radius and add pi to your angle. And so that's what we learned from these 2 polar coordinates. In fact, what we learned from these 2 polar coordinates and these 2 polar coordinates are the main 2 rules for finding equivalent points in the polar coordinate system. These last 2 sets are just providing an extra example for each of those rules. So if you take a look at this next set, we have 2 comma -pi divided by 4 and 2 comma 7 pi divided by 4. Notice that the radius is the same, but the angles differ by 2 pi, right? -pi divided by 4 plus 2 pi would take you to 7 pi divided by 4. Because like I said earlier, 2 pi is the same as 8 pi divided by 4. So if we do this right here, -pi divided by 4 plus 8 pi divided by 4 would be equal to 7 pi divided by 4. -pi plus 8 pi is 7 pi, and of course the denominator stays the same. And so since the radius is the same in each of these polar coordinates, and the angles differ by 2 pi, we know that these are going to represent the same point in this polar coordinate system. And so let's just plot one of them, and then we will know that that point will represent both of these pairs of polar coordinates. So let's do this second one here, 2 comma 7 pi divided by 4. The angle of 7 pi divided by 4, if we start at our polar axis, will take us all the way to this angle right here, 7 pi divided by 4. And that would be the same as -pi divided by 4, right? If your angle is negative, you move in the clockwise direction instead of counterclockwise like we have for our other angles. Instead of moving above the polar axis, we start by moving below. And so if we move by pi divided by 4 below, that will take us to this angle right here of 7 pi divided by 4. And then both of our points have a radius of 2. And so for along this angle, we will be at the second circle right here, which is a distance of 2 from the origin. And so our point will be right here in the polar coordinate system. Okay, and now finally let's look at this last set. We have -2 and then -pi divided by 4 and positive 2 and 3 pi divided by 4. Notice that in this case, that the radius has been negated from this point to this point. We have negative 2, but then positive 2, and our angles differ by just pi, right? If you add pi to negative pi divided by 4, that will give you 3 pi divided by 4, because pi would be the same as 4 pi divided by 4. So 4 pi divided by 4 plus negative pi divided by 4 would be 3 pi divided by 4. And so since the radius has been negated and the angle increases by pi, you know that these two polar coordinates are going to represent the same point in the polar coordinate system. And so let's just graph one of them once again. I'll graph this one, 2, 3 pi divided by 4. It's typically easier to graph polar coordinates when both the radius and the angle are positive. So that's why I'm going to choose this one over this one to just plot it more quickly. And so our angle is 3 pi divided by 4. So if we start at the polar axis, we will move in this direction till we get to this angle right here at 3 pi divided by 4. And then once again, our radius is 2. So we will be along this second circle like we have been for the rest of our points. And so that means that this point right here would represent both of these pairs of polar coordinates. Okay, so to summarize what we just learned, here are the rules that we just discussed in a more formal format. In particular, we have two rules for a set of polar coordinates, r, theta, that is going to be equal to r, theta plus 2 pi. Right? This is that first rule that we discussed. If you keep the radius the same, but add 2 pi to your angle, that will be the same point as the original point. And then our second rule, if we have r, theta, but we negate r and add pi to theta, that will be the same point as the original point. And so this is the most basic way to write these rules, but there is a more general form that I have down here. In this case, the more general way to write our first rule, instead of just having r and then theta plus 2 pi, is to have r and then theta plus 2n pi, where n is any integer. And all that means is that we can add or subtract any number of full circles. We could have 4 pi or 6 pi, 8 pi, negative 2 pi, negative 4 pi, as long as we have some number, whether that be positive or negative, of full circles or multiples of 2 pi to the angle and leave the radius alone, you're going to have an equivalent point. All right, and then the second rule, we still have negative r, we're still negating the radius, but then instead of just having theta plus pi, we have theta plus 2n plus 1 times pi. Essentially what this is saying is that you are adding a multiple of pi to your angle where the coefficient of pi is an odd number, right? That's what 2n plus 1 is doing. It's making sure that the coefficient of pi is an odd number, right? For example, if n is 0, you'd have 2 times 0, which is 0, plus 1, which would just be 1, and so you'd have 1 pi. That would give you the basic form of the rule. But if n was equal to 1, you would have 1 times 2, which is 2, plus 1, which would be 3, so you'd have 3 pi. So adding 3 pi to your angle and negating the radius will also give you an equivalent point. All right, so 2n plus 1 just represents an odd number. As long as you are adding an odd number of pi's to your angle and negating the radius, you will have an equivalent point to your original point in the polar coordinate system. Okay, so those are just some important rules to know about plotting points in the polar coordinate system. There is not just going to be one set of polar coordinates to represent a particular point. Points are not going to be uniquely represented by a set of polar coordinates. There are going to be a multitude of different ways for you to represent the same point. Okay, so that's really all there is to know about plotting polar coordinates. Now what I want to do is transition into showing you how to convert from polar coordinates to rectangular coordinates and vice versa. Because being able to convert between the two different coordinate systems can be a pretty helpful skill to know later on when you learn how to graph some polar equations. But that's for another time. For now, let's just focus on converting our polar coordinates to rectangular coordinates and vice versa. Okay, so if we want to convert between polar coordinates and rectangular coordinates and vice versa, we need to revisit our little diagram from the beginning of this lesson. Remember that I drew this angle to show you how you would plot a polar coordinate. If this is our point right here, this would be represented by this angle and this distance r from the origin. All right, but what we can do to represent this same point in terms of x and y in rectangular coordinates is to notice that this angle does create a triangle, right? And so the distance from the origin to this point right here, which is directly below our point that would be represented with polar coordinates, this distance would be represented with x. And then this height right here would be represented with y. All right, so this point, which I guess I'll just label with P, this point could be represented with two sets of coordinates. It would be equal to r theta, but P could also be equal to x comma y, right? We have our x coordinate and our y coordinate. And so what we can do to convert between the polar version of this point and the rectangular version is write some equations that relate x and y to r and theta using what we know about a right triangle. Specifically, we can make use of trigonometry and the Pythagorean theorem. And so let's start with the Pythagorean theorem. We know that for a right triangle, that the hypotenuse squared will be equal to each of the other two sides squared added together, right? So in this case, we would say that r squared is equal to x squared plus y squared. This is an equation that relates r to x and y. So this is one equation that we can use to help us convert from polar coordinates to rectangular. And if you wanted to, you could solve for r by taking the square root of both sides. That would give you r is equal to the square root of x squared plus y squared. But typically it's easier to remember r squared is equal to x squared plus y squared. And so that's one equation that we can use to convert between our coordinate systems. And then what else we can do is use our trig functions to relate this angle to the different sides of the triangle. So if you remember from trigonometry, we have the saying SOHCAHTOA. What this tells us is that sine of the angle is equal to the opposite side of the triangle divided by the hypotenuse. Cosine of theta, or cosine of the angle, is equal to the adjacent side divided by the hypotenuse. And tangent of the angle, or of theta, is equal to the opposite side of the triangle divided by the adjacent side. And so let's use sine, cosine, and tangent to relate theta and r to x and y. And so let's start with sine. We'll have sine theta is equal to the opposite divided by the hypotenuse. The opposite from the angle is y, and the hypotenuse is r. So we'll have y divided by r. And so that's one equation that we can use. Then for cosine, we will have cosine theta is equal to the adjacent side divided by the hypotenuse. So the adjacent side to our angle would be x, this side right here. So we'll have x divided by the hypotenuse, r. So cosine theta is equal to x divided by r. And then finally we have tangent. Tangent theta will be equal to the opposite divided by the adjacent. So from our angle, the opposite is y and the adjacent is x. So we'll have y divided by x. And so these three equations right here, we can use to help us convert from being in terms of r and theta to being in terms of x and y, from polar to rectangular. All right, but one more thing that we can do, typically you won't see these two equations in this form. Typically you will see them in the form where we solve for x and y. So if we multiply both sides of these two equations by r, you will get the more common form of these equations, which is y equals r times sine theta and x equals r cosine theta, right? We just multiplied both sides by r, and then I flipped the sides of each equation just so we have y equals and x equals. And so you need to know these two equations, y equals r times sine theta and x equals r times cosine theta, but you also need to know this equation for tangent and this equation for r squared. And I have those boxed in a different color because typically what's going to happen is when you're converting from polar to rectangular, you will end up using these two equations. And when you're converting from rectangular to polar, you will use these other two equations. Okay, and so let me show you what I mean by that by taking a look at some example problems where we will convert between polar and rectangular and vice versa. All right, so here's the first example we're going to look at. We want to find the corresponding rectangular coordinates for the given polar coordinates. And so we have 2 comma pi divided by 6 as our given polar coordinates. Now, the first thing that I always recommend that you do when you're converting between polar and rectangular or rectangular and polar is to graph your coordinates. Plot them on a coordinate system. And you'll notice in this case that I have our polar coordinate system, but then I also have this grid system behind it. That would be the rectangular coordinate system. And so you'll also notice that I have our x-axis labeled and our y-axis labeled. Just remember that this is where the angle is 0. For the polar coordinate system, this is where the angle is pi divided by 2. This is the angle for pi, and this is the angle for 3 pi divided by 2. All right? The angles remain the same. I just kind of merged the two coordinate systems together so that you can really see how these points are going to be the same once we convert from polar to rectangular or vice versa. All right, so let's plot this point right here. We have 2 comma pi divided by 6. Our angle is pi divided by 6, so that will take us from the polar axis to this angle right here at pi divided by 6, and our radius is 2, so we're going to be a distance of 2 from the origin. So along this angle from the origin, that will take us to this first circle and then to this second circle. So our point will be right here in this coordinate system. That is going to be our point 2 comma pi divided by 6. Now let's work on converting this pair of polar coordinates to their corresponding rectangular coordinates. And so the first thing you want to make a note of here is what your r and theta are equal to. In this case, r is equal to 2 and theta is equal to pi divided by 6. Now, when you're converting from polar to rectangular, what you want to do is use the following two equations. You want to use x is equal to r times cosine theta and y is equal to r times sine theta. Because what these two equations will allow you to do is plug in your value of r and plug in your value of theta into those two equations to get the corresponding x and y coordinate, right? X is equal to r times cosine theta, and y is equal to r times sine theta. So if we plug in the values we know, we will have that x is equal to r, which is 2, times cosine of theta, which is pi divided by 6, and we'll have y is equal to r, which is 2, times sine of theta, which is pi divided by 6. Now, cosine of pi divided by 6 is equal to the square root of 3 divided by 2. So this is equal to 2 times the square root of 3 divided by 2. Those 2's will cancel out, and so that will leave us with x is equal to the square root of 3. Now for y, sine of pi divided by 6 is equal to 1/2. So this will be equal to 2 times 1/2, which is equal to 1. So y is equal to 1. And so if x is equal to the square root of 3 and y is equal to 1, then our corresponding rectangular coordinates will be the square root of 3, comma 1. That is the pair of rectangular coordinates that corresponds to this pair of polar coordinates. And you can see that if we were to graph this point in this coordinate system. The square root of 3 is approximately 1.73. So if we go along our x-axis, hopefully you can see the squares in the background behind the polar coordinate system here. This would be a unit of 1. And then if the square root of 3 is 1.7, that would take us to about right here. And then our y value is 1, so that will take us up to this exact same point. And so you can see that the square root of 3 comma 1 is the same in rectangular coordinates as 2 comma pi divided by 6 would be in polar coordinates. They both represent the same point. Okay, so that's how you convert from polar coordinates to rectangular coordinates. Now let's take a look at converting from rectangular to polar. All right, so here's our example for converting from rectangular coordinates to polar coordinates. In this case, we want to find the corresponding polar coordinates for the given rectangular coordinates, and we have -5, 5. So the first thing that we should do here is plot this point so that we know where about our polar coordinates should be located. So if we plot this point, -5 in the x direction will take us to 1, 2, 3, 4, 5 here, and 5 in the positive y direction will be 1, 2, 3, 4, 5 right here. So our coordinate point is right here on top of the angle of 3 pi divided by 4. So hopefully when we find our corresponding polar coordinate, that will be the angle that we will have. And so let's work on converting now. In this case, what we want to do is make note of what we know. We know that x will be equal to -5 and y is equal to 5. So let's write that down. We know that x is equal to -5 and y is equal to +5. And now when you want to convert from rectangular to polar, we're going to use those other two equations that we found earlier. Instead of using x equals r times cosine theta and y equals r times sine theta, we're going to use r squared equals x squared plus y squared, and tangent theta equals y divided by x. And now the reason that we use these two equations is because each of them only uses one of the polar coordinate values, right? This equation only involves r, and this equation only involves theta. You don't find r and theta in the same equation for either of these. And that's going to make it way easier to solve for each of them individually to make up our polar coordinates. Okay, so let's use the values of x and y that we have here to solve for r and theta. We will have that r squared is equal to negative 5 squared plus 5 squared, and that tangent theta is equal to 5 divided by negative 5. Now, negative 5 squared is 25, and 5 squared is also 25, so r squared is equal to 25 plus 25, but that's just equal to 50, so I'm going to erase that, and we'll have r squared is equal to 50. And then for this equation, 5 divided by negative 5 is negative 1. So we have tangent theta is equal to negative 1. All right, now if we take the square root of both sides of this equation to solve for r, we'll have r is equal to the square root of 50. But remember that we can rewrite 50 to be 25 times 2, right? So really we have the square root of 25 times 2, and we can take the square root of 25. The square root of 25 is 5. And so we can rewrite r to be equal to 5 times the square root of 2. All right, so that's going to be our value for r. But one thing that I did forget to write is plus or minus. It's important to keep that plus or minus with your r because depending on what angle you use, you could have a positive radius or a negative radius to represent this point in the polar coordinate system. Remember that there are multiple ways to represent the same point, so we could have a positive radius or a negative radius depending on how we want to write our coordinates. But before we get there, let's solve for theta. We have tangent theta is equal to negative 1. What we can do is take the arctangent of both sides. And if you don't remember, arctangent is the inverse tangent function. So it will cancel out with tangent, and we'll just have theta is equal to arctangent of negative 1. And arctangent of negative 1 is equal to negative pi divided by 4. So we'll have theta is equal to negative pi divided by 4. Okay, and so now we have solved for r and theta. Now all we have to do is combine them to create a pair of polar coordinates that will represent this point in this system. And so this is where it's a little bit different than when we converted from polar to rectangular. The resulting rectangular point was usually right where we wanted it to be, but in this case we kind of have to make sense of what we've been given here. All right, if we have an angle of negative pi divided by 4, that means if we're starting at our polar axis, that we're going to go an angle of pi divided by 4 below the axis to this angle right here, 7 pi divided by 4. But notice that that is not where our point is that we started with in rectangular coordinates. So what that means is that if we're on this side and we want to flip or reflect to the other side, we're going to need to use a negative radius. All right, so one way that we could represent this point in polar coordinates is to use the negative version of this radius and this negative angle. So we could have this set of polar coordinates. We could have negative 5 times the square root of 2, comma negative pi divided by 4. That would represent this point right here, because we'd measure our angle, negative pi divided by 4, and then measure negative 5 times the square root of 2. That would be about 7.07 or negative 7.07. So if we're counting our circles, 1, 2, 3, 4, 5, 6, 7. I'm going to say that's right about here. Since that radius is negative, we would then flip that to the other side, which would take us to this point of negative 5, 5. So this is an equivalent point, or a pair of polar coordinates that corresponds to this pair of rectangular coordinates. But we could also write another pair. Remember our rules from earlier. We could find another pair of polar coordinates by negating our radius and then adding pi to our angle. And that would make both the radius and the angle positive, right? So if we negate negative 5 times the square root of 2, we'll have positive 5 times the square root of 2. And then if we add pi to our angle, negative pi divided by 4 plus pi will be positive 3 pi divided by 4. And these polar coordinates right here will also represent this point. Since our angle is positive, we will measure out to 3 pi divided by 4 above the polar axis. That takes us right here. And then our radius is 5 times the square root of 2, which is about 7.07, or just 7. And so we would be 1, 2, 3, 4, 5, 6, 7 away from the origin. And so that would represent the same point. Okay, so hopefully this process made sense. That is how you can take your results for r and theta and make up some different pairs of polar coordinates that represent the same point that we converted to from a given pair of rectangular coordinates. Okay, so you have to use a little bit of intuition to create these points, but that is why you graph your point initially in rectangular coordinates so that you know where your polar coordinates need to be. Okay, and then one more note. These are only 2 possibilities of an endless amount of different pairs of polar coordinates that could represent this point. We could continually add 2 pi to the angle of either one of these points and create more and more pairs of polar coordinates that would represent that same point. All right, this all comes back to that idea from earlier that there is not one pair of polar coordinates to represent each point. There are pretty much an infinite amount of pairs of polar coordinates that could represent a point. We just try to use the most simple ones in these examples. Okay, and so with that, this was the last example for this video, but if you want to see some more examples of plotting polar coordinates in the polar coordinate system and converting between polar coordinates and rectangular coordinates and vice versa, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. Alright, but if you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.